Hi, I'm Josh Gerganis, and this is Lab 4. In Lab 4, we'll be predicting the behavior of circuits containing resistors in series and parallel. We're using multimeters to measure the actual values of conventional current and potential differences in the currents, as well as examining the behavior of ohmic resistors and capacitors. The physics concepts covered in this lab include energy conservation using the loop rule, as well as current conservation using charge conservation and steady state. To start off this lab, we looked at the circuit, as you can see in the bottom right of the screen, with 2 batteries, 2 ammeters, and 2 resistors. To predict the current of the circuit, I used the equation delta V over resistance and found that the current is going to be 0.02 amps. Using the virtual kit for the circuit online, I found that this current is correct. When reversing the ammeter, as seen in the second photo, the current remained the same. Measuring the voltage of the current using the voltmeter, I saw that the voltage from the batteries adds up to -3 volts. However, since the circuit is not closed, the amp reads 0. Since the ammeter measures the current, it has little to no resistance. The voltmeter, however, has high resistance and therefore brings the circuit's current to 0. As seen in the previous circuit, I measured the potential difference between points A, B, C, D, E, F, G, and H. The sum of the potential differences between the entire circuit adds up to 0. When mapping out the previous potential differences onto a graph, you can see that the decrease in potential is over the path of the resistors, and the larger the resistance due to the resistor, then the steeper the potential difference decreases. And ultimately, the potential difference goes to 0. Different circuit elements can be measured using this resistor equation as delta V over I. The resistance over the resistor with 47 ohms is close to 47 ohms. The resistance of the 100 ohm resistor I measured to be close to 100 ohms. And then the resistance of the wire and ammeter are both 0. The times are measured for how long it takes of a capacitor to charge and discharge using a 10 and 20 ohm light bulb and a 9 volt battery. The charging capacitor of the 10 ohm bulb took about 10 seconds and the 20 ohm bulb took about 18 seconds. The times are similar with the discharging of the capacitor with the 2 different bulbs. The picture on the left is a circuit with a 1 farad capacitor and a 47 ohm resistor in parallel. Due to energy conservation, the shown circuit's voltage equation would look like so, as the delta V capacitor plus delta V resistor equals 0. And since the potential difference is measured as the charge divided by the capacitance, this equation can be rewritten as Q over C minus I times R is equal to 0. And since I, the current, is equivalent to the negative change of charge divided by a change in time, then the equation can be rewritten as seen. By solving the above conservation of energy equation, the change of potential can be written as delta V naught, or the delta V at time equals 0, to e to negative time over RC. By taking the natural log of both sides of the equation, the result can be seen as this. When putting the time and RC on one side and the delta V and delta V naught on the other, you can see that there is a relationship between the natural log of the potential difference over the initial potential difference and time over the time constant. If slope is equivalent to -1 over RC, then RC, or the resistance capacitor, is equal to -1 over the slope. And to calculate this time constant, I took the circuit kit and measured the potential difference of the capacitor at each of the following times. Then I took the potential difference into the natural log equation as found in the previous slide, and then put this into a chart over 20 seconds. Then I took the slope of the line 0.1082 and put it into the slope equation that I found in order to find the RC constant of negative 9.242. Some questions to think about at the end of this lab is, what if you did this lab in real life and actually used a real ammeter instead of an ideal simulated ammeter? And in real life, the amp reading would be lower since there is always some resistance in the ammeter. The next question to think about is, what if you were doing this lab in real life and used a real battery to change or charge a real capacitor with no resistor in the circuit? And the ideal model predicts the capacitor to fully charge instantly. However, in real life, there's always some resistance and the capacitor would take more time to fully charge. Thank you for watching.